with that, then, I think I should start my own presentation here. If someone can shift it. Yes, okay, it says that there. It says, interestingly, at UCL. I'm also at Argonne National Laboratory. At the moment, though, I'm not representing them. I'm representing myself in UCL, but I'm interested in helping them look at this technology and how they can use it at the DOE. So this first slide of mine is a set of acknowledgements. My talk is about trying to integrate quantum computing and quantum processing units with high-performance computing systems, but not for its own sake, in order to try and do new, different types of research than would be possible otherwise. I hope I can convey to you why that's actually important today. And inevitably, that's quite a challenging topic because it involves people who've got interesting scientific applications. It involves a quantum computing company. For most of the work I'm going to discuss actually is being done with IQM, which is this Finno-German company, which is collaborating directly with both us and the Leibniz Rechenzentrum, which is in Garching near Munich. And they've got quite an advanced approach to putting quantum processing units onto one of their supercomputers. So there's a bunch of people who are named here from different institutions. You can see in UK, the US, in Munich, from the Munich Quantum Valley, if you like, and we will discuss where this work has been taking us. So this particular application scenario is one that exploits a natural affiliation between the problem and the hardware, if you like, the quantum computing infrastructure that we need, because it's fundamentally around advancing our capabilities in quantum electronic structure calculations. And I want to tell you a little bit more about those. Quantum computing for quantum chemistry has been around for a fair while now and is seen to be an important area for application. Why is that? It's because conventional quantum, let's say conventional computers trying to solve electronic structure problems with molecular systems hit a wall of intractability very quickly. They're solving a Schrödinger equation for a many-body system, and the concept of the parameter of interest here being n, you could think of it as the number of electrons in the problem, or actually it's more accurately the number of spin orbitals that are used to describe the electronic configuration. The problem is that conventional algorithms scale in a nasty way with that number n. And in fact, the most accurate calculations that you could do, which are called full configuration, is worse than exponential in n. It's factorial in n. So it means that you can't get exact solutions to electronic structure problems unless you're working with very small molecular systems. So there's a whole hierarchy of approximations and so-called levels of theory that beset the field to try to look at systems of interest. And what kind of systems might we concerned with? Most of quantum computing for quantum chemistry has been confined to looking at gas phase molecules and small ones for the reason I gave earlier. But how small are we talking about? Well, if it's a gas phase molecule, it's not normally very large. And the type of molecule that might be of interest to, let's say, a pharma company, if it's a small molecule, that's a small organic compound that could easily have tens of atoms in it, and the number of electrons are then becoming very large. So a full configuration interaction calculation is impossible. We have to use approximate methods. This picture just talks about the cost of the calculations and their accuracy. And the accuracy can be important if you think you know what calculation to do, let's say to discover a new molecule. And in some cases, you might think you need that accuracy, so it's worth paying for it. But if you can't actually compute it with a conventional computer, then you're sort of in a catch-22 situation. So quantum computing is supposed to be able to solve those larger problems in contexts where they are intractable on conventional computers. And the main challenge in electronic structure theory is to do with electron correlation, how electrons interact with one another and create structures in molecules which determine their behavior. You can think of cases where you have a single covalent bond between two nuclei. That would be two electrons in a bond typically, but there are cases where you may have multiple electrons. So you could have a double bond with 4 electrons, or even, let's take a nitrogen molecule, it's got a triple bond. So there's 6 electrons crammed between the nuclei, and the correlation effects there really become very important to capture. If you don't do the calculations accurately, you can't get meaningful results. But the problem here is, as is said in the last line here, the accuracy comes with high computational cost, and the hope would be that you can deal with this on a quantum computer more effectively than you can on a conventional machine. And the reason for this that I wasn't intending to dwell on here particularly is just that if the molecular system is quantum mechanical, you represent its state by a wave function. That wave function has to be represented on a conventional, or in the jargon, classical computer in terms of 2 to the power n bits, where n, as I mentioned earlier, is that number of spin orbitals. So it's exponential in n, and you can't really handle the size of the molecules very effectively. Whereas on a quantum device, in the Hilbert space can be represented linearly, so you're suddenly going from an exponentially large problem to something that can be described in a linear fashion. So that sounds good, and that's what all the happiness about quantum computing revolves around here. But the reality is that these computers today, in this NISQ era, with a very high degree of noise and unreliability in the machines, rapidly prevents you from exploiting that potential benefit. So you have a huge amount of noise. You need to control the noise. You need to mitigate all the errors that take place on these qubit devices. And there's also a problem with the coherence time, which is the time you have available when the wave function is in its sort of superposition state, which is the state when you can exploit the quantum parallelism, which can often be in the sort of microsecond time domain or less. So your calculations can never last very long. You have to do large numbers of them. In addition to that, you have designers of quantum devices putting together topologies because they decided what would be good for them, but it's not optimal for the computations you're interested in. And that's the design of the topology can by itself trip up the application. And this is what happens quite often. So you can be, as we are, in a situation where we have access to the entire IBM cloud, which has now got up to 156 qubit chips, the Heron chips, with a plan for IBM to take the quantum to thousands of qubits by using quantum interconnects between those in the sort of sense we deal with conventional computers. But the reality is at the moment that we can't make more than a small handful of those qubits on a single chip actually play a tune. This picture shows the fidelity of those kind of qubits in the IBM cloud as it was a year or two ago. So it really doesn't matter if you've got a 127 qubit device, you can't make use of most of those qubits together. The fidelity is so low. The struggle is to be able to reduce the size of the calculation in terms of the qubits that you need to get onto the device, and all the time controlling the noise and dealing with error mitigation. So there's this problem, which is paradoxical and ironic, that you've got this quantum device, but what you want to do is touch it as it were, as infrequently as you possibly can, and make sure that when you do use it, you're really using it without being overwhelmed by the noise. And that means the quantum capabilities are rather diminished. But if you try to bring those quantum capabilities into an interesting problem that's not a single gas phase molecule, well, then you had better be interacting with a conventional computer which can handle those scale of problems much more effectively. And that's what this slide is reminding us about. Quantum hardware is on its own in a cloud, unable to really support bigger and interesting scientific problems. You have to shift data. You have all these problems of the difficulty of moving data from the classical compute to the remote site, and then the latency issues and so on. So a lot of people who start out in quantum computing just have a laptop and they try to run qubit jobs on, say, an IBM cloud or a public version of it, and that really restricts anything they can do. What we're really after is the picture on the right-hand side where the two things are up close and personal, and that's the sort of thing that we're talking about here in IAM, where I would say that LRZ is one of the world leaders in trying to make this sort of thing work with the IQM devices that I spoke about earlier. In much of the work I'm talking about quickly here, it's 20-qubit devices, but IQM has now got a 54-qubit series of devices called Emerald, which are coming on stream. And the interesting thing here about the architecture is that this is a square topology, whereas IBM's is heavy hex actually restricts, as I was saying implicitly before, the capability to do longer range computations with more qubits. But here we've got the so-called IQM QX chip, 20 chip, and we're able to link it with the SuperMOOC NG machine, which is sitting at the LRZ facility and has been there for quite a long time. That machine has about 311,000 cores on it and originally entered the top 500 around number 8 many years ago. So it's a fairly powerful machine, and you've got one small qubit connected into it now. And the kind of problems we're interested in doing now are getting away from a single molecule, although I'm showing you something a bit like that here, into a multi-scale environment. And that's what I'm building up to here. One of the problems we've been interested in is understanding the way in which protons hop between water molecules in bulk water. Note, I'm not talking about a single water molecule anymore. I'm talking about a group of these molecules and atoms within them. And in fact, I'm going to talk about an assembly of bulk water inside which we may abstract a component of it and look at the quantum mechanical aspects there. So in this area, the interest about water is it's always a fascinating substance. It has a very high water conductivity, and that's a reflection of the mobility of the proton that can hop across adjacent water molecules at tremendous speed. It's not really diffusing a single proton. It's one proton hops between two water molecules, and then another proton goes between another adjacent pair and propagates, and it's called the Grotthuss mechanism. So it has a lot of important aspects, and today even not all the things are agreed about this. There are different structures for the cation that's involved, which has a proton sandwiched between two water molecules or three, and in the Sundal case, it's a planar molecule. In the eigencation, it's actually more of a pyramidal structure. So you may be interested in computing the rate at which the proton transfers across this, and in that case, you have to do electronic structure calculations of the potential energy barrier as a function of the separation between the water molecules with the proton going between them. This scale of calculation is amenable to a quantum computer in the way I'm trying to describe here, but it's in the context of the bulk fluid, because water molecules, when they club together, form water, not just individual water molecules, through the interactions they exhibit. And some of those we will connect to through the multiscale element. If you're into multiscale modeling and simulation, you'll be familiar with the idea that you can connect different levels of, as it were, physical representation of a system, and you need to do some parts of the problem in more detail, others in less, and you couple the two things together. And that's the spirit in which we're now adding a quantum computational calculation into a multiscale modeling environment. So a large part of this simulation is done on the conventional computer. And I can make that calculation pretty big. And I will just hive off the part of it that matters for an accurate quantum calculation where there's an important electron correlation effect. And that's what we're doing here. And we use a technique called the QMMM method, quantum mechanics, molecular mechanics. In 2013, 3 American theoretical chemists won the Nobel Prize for this methodology that dates back already to the 1970s, when it was very difficult to implement on existing computers. So it's a representation of a simulation, it's a simulation of a piece of matter where you break the parts up into a quantum domain where the electronic structure matters, and an external domain which is treated by classical mechanics. No time here to inflict all the mathematics of this on you in detail, but you understand there are two parts of this representation, the larger classical component and the internal quantum one, and they have themselves the issue of how they're coupled together. And inside that, what we're trying to do in these calculations is hive off the part of the calculation that we really want to do accurately and put that onto the quantum device. So in the situation I described of this Tyndall cation, I've got a proton that's hopping between 2 water molecules. And actually, we have developed projection-based embedding methods here, which can abstract from this complex a small part of the molecule that's the one where all the action is on the quantum mechanical level, and we can take that out of the bigger picture of the quantum mechanical representation that's done on the classical machine using density functional theory and do a wave function calculation of what that proton is doing as it moves across. And so this is the sort of thing we're doing here. We use an algorithm which is quantum selected configuration interaction. We've gone beyond the variational quantum eigensolver these days because it has too much noise and error correction problems associated with it. But what we're effectively using the quantum device for is to represent the wave function, as I described earlier. That's where the quantum computer is particularly good at doing the representation effectively, and we can sample that wave function on the quantum computer and bring back the sampled results and do the rest of the calculation on the classical device. We use a whole battery of techniques to make this work effectively. In the time available here, I'm not really going to go into it in detail, but so-called tensor networks are being used at all stages here to expedite parts of these calculations. And there's a workflow involved which goes between an MD code called LAMPS that then shifts stuff to a Python-based self-consistent field electronic structure calculation, and from that, the electronic part that we want to put from the qubit Hamiltonian we compute in the projection-based embedding is then moved onto the quantum device. Sampling is carried out according to a strategy that you define, and then the results shipped back to the conventional computer. So this is the sort of thing that we're talking about doing here. We've recently put a preprint into play about this, which shows the benefits of using QSCI to do some of those calculations. And the slide, if you can see it clearly, you may not be able to see the shading down at the bottom, but many of the calculations at QSCI at the level we're doing those are actually within so-called chemical accuracy, which is important for calculating things like the activation energy for the proton hopping, and from that rates, and then ultimately conductivity and other things. So the next steps in an approach like this are to build the more elaborate, complex steps into the multi-scale workflow. It's got all the bits I mentioned earlier, but the extent to which you have feedback between the conventional computer and the quantum one, and the time stepping that we need to put into play have to be built into this description, and all of those things can be gradually scaled out. The merit of the approach we have is that every part of the algorithm is actually very nicely scalable. So as qubits become, and quantum devices become more reliable, we can get them going onto bigger machines. Bigger portions of the molecules can be used there, larger parts on the classical device. So that's a picture of the kind of thing we're interested in trying to do and currently can support on these coupled quantum classical devices. And I think with that, I should stop and potentially take one question if anyone has something, but I'd rather not. I'd rather move now to Cécile to come up and take over with her presentation of what's going on in hardware and maybe the path towards fault-tolerant computing, yes?
Exactly. Well, thank you.
Thank you.